Alrighty, so good morning. Today we're just going to discuss a few key points on radiation and radioactivity. So I'm going to highlight some key terms here for us as we work through this first portion here of our little OneNote summary. So radioactivity involves all three types of radiation, those being alpha, beta, and gamma. Radioactivity is the spontaneous breakdown of the nucleus of unstable isotopes, another set of key terms there, and it results in the emissions of particles or rays. So remember from earlier in the term, isotopes simply refers to elements or atoms that have an uneven number of neutrons and protons. Typically, or normally, an atom has the same number of protons as it does neutrons, as it does electrons. All of those numbers are consistent. An isotope is when we have a different number of neutrons. It could be more, it could be less than the protons, but it's important to note that it's different. These isotopes can be stable, but some are unstable, and it's the unstable isotopes that we're referring to when we discuss radiation and radioactivity. It results in the emissions of particles or rays. So that's a key point that links in to our table here in the bottom left-hand side. Each type of radiation has different characteristics which are important to explain how they behave. The characteristics of each of these types of radiation help us to explain how they behave when exposed to different things. So this information I've actually gathered from our ClickView video that we viewed in the radiation lesson. I'll just run you through some key points here. So on the very left hand side, you've got the characteristics, and we're going to highlight here what the different characteristics are for each of these types of radiation. So alpha radiation is made up of 2 protons and 2 neutrons. Remember that, I'll just highlight here our atomic mass units, or the mass. Electrons don't have a mass. The only subatomic particles that are counted when we discuss the atomic mass of an element or an atom are the protons and neutrons. Their relative atomic mass is 1. So given that we've got 2 protons and 2 neutrons, each of those is worth 1 mass unit, so 2 plus 2 gives us 4. You can see there, in comparing this to our beta and our gamma radiation, that alpha is the heaviest. So it's got an atomic mass of 4. It also has those 2 protons, which are really important, and that gives us an indication of its charge. Remember that neutrons are neutrally charged, so they don't have a charge. We've got 2 protons there, which we know are positively charged, so we've got a charge of positive 2. The speed is slow. So the speed at which this radiation moves is really slow. And remember that all of these have a speed because they result from the spontaneous breakdown of the nucleus of an unstable isotope. Spontaneous breakdown, in your head, remember spontaneous is out of nowhere. You can't predict when it's going to happen. Breakdown, imagine almost like mini little explosions. So if you've got this huge unstable isotope, what's happening when we have radiation is spontaneously parts of that nucleus are breaking away into different types of radiation. Alpha radiation, it breaks away as 2 protons and 2 neutrons. Let's link that over here. I'm just going to grab a red pen. So our alpha rays here. This diagram provides a really nice summary of the behavior of each of our types of radiation. I'm going to just pick an orange here to run with our little red sort of thing. Our alpha rays, or our alpha radiation, behave in this specific way. Now, by the way, this here represents a negative charged magnet. This here represents a positively charged magnet. Our alpha rays are quite heavy, so we know they've got an atomic mass unit of 4. As they're moving away from this radiation source, firstly, you can see that they're heading over to the left-hand side. They're heading over to this negatively charged magnet. That's because they are positively charged. They've got a positive charge of 2. We know that opposites attract, hence why our alpha rays are heading over to that negative terminal. Why are they moving at such a slow angle, or why are they not bent in a way like our beta rays are? Well, that's because they are slow, because they are heavy. So they're moving over towards that negative terminal. They're doing so slowly, which is why we only have this very slight bend in their movement. So let's compare that to our beta. Our beta radiation, I'll just grab a little green highlighter. Our beta radiation is made up of just 1 electron. 1 electron, we know that that has a negative charge of 1. We mentioned before as well that electrons don't have a mass. Beta radiation is made up of an electron, hence it doesn't have an atomic mass. So this is really lightweight as a point of difference. That also allows it to move really quickly, which is another important component. So these beta rays have a negative charge. They've got a negative charge. That explains why they're moving towards this positive terminal, this positively charged magnet. They are much lighter than our alpha radiation, hence why they can move around and they bend really quickly. They're really quick in changing direction and moving towards this positive source. So that's why their pathway looks as it does. The last little one that we'll cover is our gamma radiation. So our gamma rays. So you can see the ones that are heading straight up there from that radiation source. They're made up of electromagnetic radiation. So they're actually part of our electromagnetic spectrum. They're not made of anything in particular. They're not made of electrons. They're not made of protons. They're just pure radiation. Because of that, they don't have a charge. So it's simply just 0, it's neutral. They don't have a charge. They also don't have a mass. And they move really quickly. So at the speed of light, they're the fastest of the types of radiation. But an interesting thing you can see is that these gamma rays are just heading straight up. They're not influenced at all by our positive or our negatively charged terminals. Why is that? Well, that's because they don't have a charge of their own. They don't have a charge. They're not influenced here by the positive or the negative terminals of these magnets. Oh, there's the bell. That was good timing. That is actually the end of our little summary and explanation here. I hope that helps to clarify a few things for you. Of course, if you have any further questions, please just post a little question in our Teams and I'll get back to you very, very shortly.